Okay, so we're going into chapter 1, section 2 here. And again, the student outlines will be available for you along with these slides as well. Okay, so in 1.2, we're looking at types of data. And a key concept from 1.2 is that a major use of statistics is to collect and use sample data to make conclusions about populations. Right, that's one thing we talked about in 1.1. And I put up the definitions here again. So population, complete collection of all measurements or data that are being considered. Typically the complete collection of data we would like to make inferences about. We would like to get data about and then make some inferences, make some conclusions, take some action based on the data that we have. And then recall the different categories, so census versus sample. Census, a collection of data from every member of that population. Sample is a sub-collection of members from that population, so from that same population. Okay, so two definitions. We have parameters and statistics. Okay, so parameter is a numerical measurement describing some characteristic of the population. Okay, so again, I included these definitions here so you could easily connect parameter and statistic. So statistic, numerical measurement describing some characteristic of just the sample. Okay, so if we're talking about the whole population, we'll use parameters. If we're talking about just the sample of the population, but just the sample, we use the word statistic. Okay, so those are the definitions here. So connect between parameter and population, and then statistic and sample. Different types of data here. We have quantitative or categorical, and quantitative, so quantity is in that word, or numerical consists of numbers representing counts or measurements. So examples of quantitative data is actual ages, so you have a number for each respondent, the weights of hamsters. You're, for some reason, to decide to weigh hamsters. So that's numerical data because you have an actual grams or pounds related to each of those hamsters. So it's quantitative or numerical data. Alternatively, we have categorical or qualitative or attribute data. Usually I won't use attribute, but categorical or qualitative, I think you'll see more. So that consists of names or labels, and then so not numbers that represent counts or measurements. Okay, so categorical data could be the species of hamster. So that's not telling us anything about a number. So also shirt numbers on professional athletes. So he, she, or their number 34, that doesn't mean that they're the 34th drafted or they're the 34th best on offense, right? It's just a kind of a random number that athlete is assigned. So that's actually an example of a categorical piece of data. Okay, so that's kind of tricky. The quantitative, the age means something, a weight means something, but shirt numbers don't mean anything really numerically. They don't tell you about the actual quantity. Okay, so that's an example of categorical data. Okay, so also we have this idea of discrete and continuous. Quantitative data now we're on. So we had quantitative and categorical. Within describing quantitative data, so we had the weights of hamsters, we have the ages of respondents. This kind of data can either be discrete or continuous. Okay, discrete data is the result when data values are quantitative and the number of values is finite or countable. And I'll read you these definitions and then we'll talk more about the specifics. So an example here is the number of tosses of a coin before getting tails. Okay, so it's discrete data. You can toss the coin once, twice, 3 times, 4 times, 5 times, and you have these discrete values of 1, 2, 3, 4, 5. Okay, so that's discrete data. It's countable, it's finite. Okay, and then for continuous data, this is the result from infinitely many possible quantitative values, where the collection of values is not countable. So if we were saying the lengths of distances from 0 to 12 centimeters, okay, so it's all of these lengths in between. It's a continuous scale of all the lengths between 0 and 12 centimeters, for example. And I'll show you another slide about this to picture it. So you might see different graphs like this. And so this is how we can separate in our heads discrete versus continuous. Discrete, again, we have these countable finite measurements. So for example, this bar graph on the bottom is an example of discrete. But for the line graph right here on top, we have a continuous set of values. And then on the second graph represented here, Top is an example of our continuous data, and then here we have an example of discrete data. So continuous, resulting from infinitely many quantitative values where the collection is not countable, versus discrete, we can count each of those values. So again, these are different examples. Okay, and to reiterate one more time, so we have our quantitative and categorical data. When we're talking about discrete and continuous, this is ways we can categorize our quantitative data. And these more definitions to start getting used to, and the example should help you understand what each of these means. So there's 4 levels of measurement. So nominal, ordinal, interval, and ratio. So nominal, characterized by data that consists of names, labels, or categories only, and the data cannot be arranged in some order, such as low to high. So an example of the survey responses of yes, no, undecided. We can't rank these as low to high, right? So nominal data consists of names, labels, and categories such as yes, no, undecided. The next level we'll talk about is ordinal. So this involves data that can be arranged in some order, but the differences that could be obtained by subtraction, for example, between data values either cannot be determined or they're meaningless. So a good example here are course grades. We can put these in order. So A minus, B plus, B, C, these are in descending order. However, to add some value between A and A minus and B plus, we can't do that easily. We can't just subtract A minus half an A equals A minus, for example. Okay, so that's ordinal level of measurement. Okay, the third kind we'll talk about is interval data. So this involves data that can be arranged in order, and the differences between data values can be found and are actually meaningful. However, there is no natural zero starting point. So this, the example of years is a very good example of this. We can have years, we can subtract between 1,000 or 2,000 minus 1,000 years equals 1,000 years. So we can subtract, and we do have meaningful intervals between the data points. So there's no natural starting point for years related to how we count the calendar years traditionally. Ratio is the 4th type. So it's data that can be arranged in order, and differences can be found and are meaningful. Okay, so that's another check. There is a natural zero starting point, though, for ratio level of measurement. Okay, so the 0 indicates that none of the quantity is present. So if we're going back to our interval example at year 0, does that mean that there are no years there? No, right? So for ratio, one example here is the class times of 50 minutes and 100 minutes. So data can be arranged in order. The differences can be found and they are meaningful. So this class is 50 more minutes. The 100-minute class is 50 more minutes than the 50-minute class. There is a natural starting point, right? So at 0, we have no class at all, right? So 0 indicates that none of the quantity is present. Okay, so those are the 4 different levels. So to summarize them here, nominal, categories only; ordinal, categories with some order; interval, there are differences that can be meaningful, but there's no natural 0 point; ratio, we have meaningful differences between the data, and there is a natural 0 point. Okay, another topic here in 1.2 is big data and data science. And in the picture here, this is an example of a supercomputer from IBM. So big data, it refers to data sets that are so large and so complex that their analysis is beyond the capabilities of traditional software tools. So there's a lot of big data that goes on, especially in the San Francisco area. So there's a lot of startup companies and companies that use these supercomputers to try to ultimately make money, right? And try to predict based on a set of data what inferences they can make. And because the data is so large and so complex, some companies actually use supercomputers to work on their statistical analysis. Okay, so we also have data science that you may have heard of. This involves applications of statistics, computer science, and software engineering, along with some other relevant field. So for example, I have a colleague who considers himself a chemist and a data scientist. So he'll look at large amounts of data, chemistry-related data, and make inferences about that. So he's sort of a data scientist, statistician, and a chemist. Okay, so another set of terminology here is the idea of missing data. And a data value is missing completely at random if the likelihood of it being missing is independent of its value or any of the other values in the data set. Okay, so one data point is missing, it's just a random one. It wouldn't impact, hopefully, what conclusions we're making from that data. Just a very random data point, it happens to be missing. Okay, there's also data values that can be missing that are not at random. So that's if the missing value is related to the reason that it's missing. Okay, so ideally we don't have any biases in our data. If a value is missing, hopefully it's at random and it's not something that we're intentionally trying to leave out of our data set. There's also ways for correcting for missing data. For dealing with missing data, it's pretty common to just delete all the subjects that have missing values. Okay, that's one way to take care of it. And hopefully that's not inducing some amount of bias in which cases we're deleting, which data points we're deleting. We can also impute missing values. So we need to be careful with this too. When we impute a missing data value, we substitute a value for that missing data point. Okay, so that word impute, assigning a value to something by inference. So we need to be really careful if we're thinking of doing this. We want to be implementing all these practices without any amount of bias for the data that we're looking at. Okay, so that is the end of 1.2. Look out for another lecture on 1.3. I hope you're all doing well and taking care of yourselves this first week. There can be a lot going on this first week to get used to, getting used to Canvas, setting everything up. So keep me posted, and I will talk to you all very soon with 1.3.